Alright, so let's proceed to the part 3 of the question about the cube roots of unity or roots of unity. So, this is the part 3. It says that deduce that the limit of this series is equal to this. Alright? And in our question, we have said that the sigma of n, the sum of n of x, the sum of n of x is equal to this. So that is actually this one a while ago, right? And then we have shown that this one, or this is the definition, and we have shown that this is true in the part 2 of our question. Now, the question now is that we would like to show that this one, let me just, that this portion, okay, we would like to show that that portion there is equal to this. If n is approaching to infinity, meaning to infinite number without bound, and that portion there, this one here is exactly similar to this. That's exactly similar to that. Correct? So therefore, what are we going to do is that we need to use this to be able to get this. And what is this one? That is actually 1/3 of this expression. Okay? Because we just divided by 3. Let me just remove this one here. Okay? So this series is equal to this, okay, as n approaches. But this one now will change because it's up as n approaches to infinity. So I will just put here infinity like that. Okay? Now, however, we know the definition of this. And what's the definition of that one? This one here. Okay? So we know that this is equal to 1/3. The s of n of x is that. Let me just copy that. N to 0 of 3n of, I will just put a sigma, like outside, of x to the n over n factorial. Okay? So this portion is this one. Plus, this one here is the sigma of omega x to the n over n factorial. Okay? And then this portion here, by using this definition, is the sigma of omega squared x. Okay? Omega squared x to the n over n factorial. So there you go. Then let me just close this with a parenthesis. Okay? So it's very intuitive. It's very intuitive because we're just using the definition of s of n of x, which is this one. But what is this one here? How shall we go on? How shall we simplify this? Now, in your MF10, in the formula booklet in further maths, the MF10, e to the x, the Maclaurin series, let me just write that word. Okay? Let me just write that word, Maclaurin series. Maclaurin series. Alright? In Maclaurin series, according to Maclaurin, e to the x is approximately equal to 1 plus x squared 2 factorial plus and so forth and so on, plus x to the n to n factorial plus and so forth and so on. Meaning, if x is a very small number and n is approaching to infinity, e to the x is approximately equal to this. If you want to prove this one, please watch my video about Maclaurin series. So this one now, we will apply this property or this mathematical principle here. I want you to notice this portion here. Okay? I want you to notice that e to the x is actually the sum of this. But what is this one? That is actually exactly that. Okay? They're actually the same. So therefore, what are we going to do? So therefore, this portion is that. So that is actually 1/3. Okay? That is actually 1/3 of this is the definition of e to the x. Alright? What about this one? So this is now omega x to the n. Omega x to the n. So what is that? That is the definition of e to omega x. Okay, so that is the definition of e omega x. Alright? And what is this? That is the definition of e raised to omega squared x. Alright? Now, I want you to notice this one here, that remember that the omega, in the part 1 and 2 of the question, omega is the root of the cubic form, of the cube root of unity. So omega is the root of z cubed minus 1 equals 0. Right? And what is that omega based on our computation a while ago? So we have said this one. So we have said in the previous video that the z cubed minus 1 equals 0. This is our root. Alright? And that is our omega. And this is our root. And that is our omega squared. Alright? So, however, here, and remember that this is another way of writing, the, what do you call it? The complex number. Okay? That's another way of writing complex number. So therefore, this one here, let me just plug in. Okay, since omega is equal to -½ plus the square root of 3 over 2i, then this portion here will be 1/3 e to the x plus e. We are just putting this into there. Okay, we're putting this one into there. E raised to, I will use another color just to distinguish that, -1/2 plus square root of 3 over 2, that is I, that is x, okay, plus e. Alright, however, it's still visible on the screen, okay, e. Your omega squared is the conjugate of this one, that's the omega squared. So that is a -1/2 minus square root of 3 over 2 I x. Okay? There you go. And what are we trying to prove? We're trying to prove that this is equal to this. That is what are we trying to prove. So let me just, okay, wait, I have here. So what we're trying to prove is that that portion is equal to that. Okay? So there you go. It's almost there. See, 1/3 is there. E to the x is there. So meaning this portion here of the question, this portion of the original question that we have, is actually equal to that. Okay? So we want to deduce this to make it like this. Okay? How shall we do that? This is just like a magic. It's not really that a big problem. E to the x plus this one is equal to what? That is equal to e to the -½ times e to the square root of 3 over 2i. Yes. So x there and x there, plus this one is e to the -½ of x, and then this one is e to the negative square root of 3 over 2 I of x. Alright? So, like that. So I want you to look at that. It's almost there. So, as you can see from here, that this portion is common to the two of them. And look at our question. This is common. Okay? So, what shall we do? So we need to factor out this part here. So let's try to do that. So you have the 1/3 e to the x. Again, if you got dizzy with this question, all you just need to do is just to relax for a while and just watch the video again. Okay, watch the video again until you would be able to get used to it. Times e, but we're just factoring this out. The square root of 3 over 2ix. Okay, this is now plus e negative square root of 3 over 2ix. There you go. There you go. Almost there. Now, can you visualize now what's going to be the next step? So look at look at this one and look at this process here. Look at this final answer. What is the next step? So this we got already. We got it from there. This almost there. Okay? What is this one? See? It becomes x is square root of 3 over 2. What is that? Do you remember something like this one? What is that format? Okay? What is that one? Now, if you're gonna look at this, remember that the z is also written as ei theta. And remember that the what do I call this one? De Moivre's theorem. The De Moivre's theorem, we said that you have here the z. Sorry, it's not visible. I'm very sorry about it. In the De Moivre's theorem, we have said that the z plus the z to the negative 1, which is equal to 2 cosine theta. Correct? 2 cosine theta. But what is this one in that form? The e to the I theta plus e to the negative I theta gives you 2 cosine of theta. Right? And I want you to notice this form. I want you to look at these two. They're actually the same. We're in the theta, where it shows that the theta here is square root of 3 over 2. Right? So what is the meaning of that? The meaning of that now is that this, we can say that e raised to the square root of 3 over 2 ix plus e negative square root of 3 over 2 ix is actually this portion here, and that's actually equal to 2 cosine of the angle. And what's the angle? The square root of 3 over 2 x. Alright? Therefore, there you go. Therefore, our final answer now is 1/3 e to the x plus 1/3 times that is 1/3 times 2 here, because this is 2 cosine of this, so that's going to be 2/3 of e negative half x, alright, times cosine of the square root of 3 over 2x, which is the original question, which is the one that what we are trying to prove. Okay, so this is our statement that we're trying to prove a while ago. Let me just look at that question, the specific question. Oh, I can't find it. Oh, there we go, here. Well, anyway, just try to, I can't find the question now. Oh, there we go. This one here. Alright? So this one is exactly the same thing to what we're trying to prove a while ago. Okay, so I put it here, there. So perfect. Thank you for watching this video, and see you on the next videos about further mathematics.